Hi everyone, today we'll be taking a look at a question on vectors. So in this question, you are given an equation of a plane x minus 2y plus 2z equal to 12, and the position vector of A is given by 2, 1 minus 3. Part 1 of the question says you are supposed to find the coordinates of the full perpendicular end from point A to P. Okay, so first let's rewrite the equation of the plane into the scalar dot product form, and the position vector in the column vector form. We can also draw a simple diagram to illustrate this particular scenario. It will help us in our visualization. So we have point A, and this is the full or perpendicular of plane P, and the normal vector is given by 1 minus 2, 2. I would think that in this particular scenario, the best way and more efficient way is to construct the equation of this particular line, which passes through point A and parallel to the normal. So we will be using this particular line to intersect the plane. That should give us the position vector of point A. So let's construct the equation of the line AN first. So if it passes through the point A and parallel to the normal, which is given by this. So we can also say that let ON be equal to 2 plus lambda, 1 minus 2 lambda, minus 3 plus 2 lambda. Okay, reason is because point A we can see from the diagram that it's also lying on the line. So when it's lying on the line, the point A will take on the equation of the expression here given a specific value of lambda. So on top of that, we can also see that ON will also lies on the plane. So basically, we can just substitute the entire expression here into the equation of the plane. That will be equal to 2 plus lambda, 1 minus 2 lambda, minus 3 plus 2 lambda, dot with 1 minus 2, 2. So we can just simply evaluate this particular expression here, then we can find the value of lambda. And with this value of lambda, we can substitute back into here to find the full perpendicular. So here we get 2 plus lambda, minus 2 plus 4 lambda, minus 6 plus 4 lambda equal to 12. So we get 9 lambda equal to 18, solving lambda equal to 2. So plug the value of lambda into ON. So ON we will get 4 minus 3, 1. Okay, and since the question required us to find in terms of the coordinates, so we can just say coordinates of n is 4 minus 3, 1. Okay. So next part of the question says, hence determine the coordinates of the reflection of point A in P. So the point that we really could find is, we just call it A prime. So basically from the diagram, we can see that ON actually is the midpoint between A and A prime. So we can actually make use of our ratio theorem to find this particular point. So first step, we can just let A prime be the required reflected point. So making use of ratio theorem, ON will just be equal to lambda OA prime plus mu OA over lambda plus mu, where we can say that this is lambda, this is mu. And since this is the midpoint, we can say that the ratio is just 1:1. So we get OA prime plus OA over 2. Okay, re-expressing this particular expression, we will have OA prime equal to 2ON minus OA. Substituting the values in, 4 minus 3, 1. OA will be 2, 1 minus 3. So we'll end up with 6 minus 7, 5. So coordinates of A prime will be 6 minus 7, 5. Okay, so let's take a look at part 2 of the question. So part 2 of the question says you are supposed to find the Cartesian equation of the plane such that the perpendicular distance from each plane to P is 15. So from this particular question here, I can actually extract out two pieces of information. So the first information is the plane must be parallel to each other. Because if the plane are not parallel, that means they will definitely intersect somewhere in a line. And the perpendicular distance will simply be 0. So the second information I can see is actually they are supposed to have two planes that are parallel to the original plane. So assuming that this is the original plane, so the one of the plane that I need to find 15 units away is here, and the other one will be at the bottom. So let me just illustrate this particular scenario with a diagram. So this is the original plane. So P, which has an equation of 1 minus 2, 2 equal to 12. So one of the plane that I need to find is above the original plane. The other plane will be below the original plane, 15 units away from each. So we can also see that the equation of the planes that I need to find will also take on this particular form, because they all have the same normal. Maybe I can just call it Q, and the Q is the value that I need to determine. So for finding distances between two planes, actually I have a particular formula. The formula is given by this particular here. So the distance D is equal to P1 over modulus of N1 minus P2 over modulus of N2. And for N1 and N2, they must be pointing in the same direction. So let's rewrite this formula here. So we have D equal to modulus P1 over modulus N1 minus P2 over modulus N2. All right. So in this case, the distance is given by 15 units, so we can substitute 15 in. For P1 or P2, it doesn't matter whether you choose 12 or Q, it doesn't matter. So maybe I can just choose Q. Modulus of N1 is the modulus of the normal. So it will just be 1 square plus 2 square plus 2 square. So this one will just be the P2 of the original plane. So I got 1 square plus 2 square plus 2 square. Right? So basically, we just need to evaluate this and solve for the value of Q. I will expect to have two answers for Q because of the modulus. So I got 15 over Q over 3 minus 12 over 3. So multiplying 3 over to the other side, I got 45. Get rid of the modulus, I will have a plus minus 45. Solving for Q, I will get 57, or Q equal to minus 33. Right, so once we have found the value of Q, 57, and Q equal to minus 33, I can just simply rewrite this Q to be 57, and this Q to be minus 33. And the corresponding Cartesian equation for each of them will just be x minus 2y plus 2z equal to 57, and x minus 2y plus 2z equal to minus 33.